Hello everyone, and welcome to a new episode of the Virtual Lab series of video blog presentations on various diverse scientific computing topics. As you can see here, the title of today's presentation is on the role of density functional theory and molecular dynamics computational techniques in predicting the mechanical properties of materials. This presentation is provided by Virtual Lab, the company behind the development of the Materials Square online platform. Materials Square is entirely dedicated to assisting and encouraging researchers from across the world to perform atomistic computational simulations on a wide range of materials science and molecular chemical modeling applications, directly via our integrated powerful cloud computing resources. Being entirely online-based, and executable via any basic web browser interface on any device with internet access, the Materials Square platform makes it possible to execute such complex simulations and calculations without the need to install any complicated scientific code locally on your machine, and without the need to have expensive supercomputing clusters at your immediate disposal. Our supported atomistic simulation functionalities and solutions are mainly based on well-established scientific computational techniques such as density functional theory and classical molecular dynamics, and have a very broad range of useful applications in computational chemistry and materials science R&D, which are thus ideally suited for both industrial and academic users from around the globe. We invite our viewers to please consult our products and services offered via the Materials Square platform by visiting its corresponding website, which is www.matsq.com, as noted also in the video description below. So, let us begin our main scientific presentation of today. The mechanical properties of materials refer to the way materials behave when subjected to forces, or more generally, when they interact with their environment in a way that changes their shape, size, or structure. The mechanical properties of a material are crucial for its selection in various engineering and scientific applications. Here are some of the key mechanical properties. 1. Strength. This refers to the material's resistance to deformation or fracture when subjected to a force or load. There are different kinds of strength, such as tensile strength, resistance to pulling apart, compressive strength, resistance to being squeezed together, and shear strength, resistance to sliding forces. 2. Elasticity. This is the ability of a material to return to its original shape and size after the removal of stress. The degree of elasticity is defined by the elastic modulus, Young's modulus, which is the ratio of the stress applied to a material to the strain it experiences. 3. Plasticity. This refers to a material's ability to deform permanently, without breaking, when stress is applied. Once the yield strength is exceeded, the material will deform plastically. Ductility and malleability are aspects of plasticity. Ductility is the ability to be stretched into a wire, while malleability is the ability to be flattened into a sheet. 4. Hardness. This is the ability of a material to resist deformation, usually by indentation. Hardness tests involve pressing a harder material into the surface of the test material and measuring the depth of the resulting indentation. 5. Toughness. This is a measure of how much energy a material can absorb before it fractures. It's a combination of both strength and ductility. A tough material can withstand stress and strain. 6. Fatigue strength. This is the maximum stress a material can withstand for a specified number of cycles without failing. It's important for materials that experience cyclic loading, like bridges or aircraft wings. 7. Creep resistance. Creep is the slow, permanent deformation of a material under a constant load or stress over a long period of time. High temperatures often accelerate creep. Creep resistance is a crucial property for materials used in jet engines or power plants, which operate under high stresses and temperatures. The mechanical properties of materials are influenced by their atomic structure, the types of bonding between atoms, the arrangement of atoms, and the presence of defects or dislocations in their structure. Factors like temperature and strain rate also affect a material's mechanical behavior. Understanding the mechanical properties is crucial for material selection in different applications, from the construction of buildings and bridges to the design of aircraft and microchips. Let's now discuss more in detail how the density functional theory ab initio computational technique can be used to compute the mechanical properties of materials. Density functional theory, DFT, is a computational technique used widely in physics and chemistry to investigate the electronic structure of many body systems, particularly atoms, molecules, and the condensed phases. DFT can be used to predict the mechanical properties of materials in some of the following ways, for example. 1. Calculation of elastic constants. The most direct application of DFT to the mechanical properties of materials is the calculation of elastic constants. This is done by straining the material, changing its volume or shape, and calculating the total energy at each strain. The second derivative of the energy strain curve gives the elastic constants, which provide fundamental information about the material's response to mechanical stress. 2. Prediction of phase diagrams. By combining DFT calculations with thermodynamic models, like the quasi-harmonic approximation, one can predict phase diagrams of materials. These diagrams show what phase a material will be in, solid, liquid, gas, or plasma, at different temperatures and pressures, which is crucial for understanding its behavior under different conditions. 3. Investigating plastic deformation and dislocations. DFT can be used to study how atoms move when a material is subjected to stress beyond its elastic limit, leading to permanent deformation. This involves calculations of so-called Piles stress, the minimal shear stress required to move a dislocation, and Piles barriers, energy barriers to dislocation motion. 4. Computing phonon spectra and thermal properties. The vibrational properties of a material can be computed by calculating the forces between atoms from DFT and then solving the phonon-Schrödinger equation. These phonon spectra provide information about the thermal conductivity and heat capacity of the material. 5. Understanding fracture mechanics. DFT can be used to study how and why materials fail when subjected to stress, including the process of crack initiation and propagation. To compute these properties, DFT uses the fact that the total energy of a system can be expressed as a functional of the electron density. DFT aims to find the ground state electron density that minimizes this energy. This density is used to compute the properties of interest. In principle, DFT can predict these properties with high accuracy, but in practice, approximations are made for the exchange correlation functional, which introduces some error and impact the accuracy of the predictions. Researchers must therefore be aware of these limitations when interpreting DFT results. Let's now describe the alternative case of how classical molecular dynamics computational techniques can be used to compute the mechanical properties of materials. Molecular dynamics, MD, is a computer simulation technique that models the physical movements of atoms and molecules. The atoms and molecules are allowed to interact for a fixed period, giving a view of the motion of the atoms. In mechanical studies, molecular dynamics is used to simulate and study the mechanical response of a material at the atomic scale. Here's how this is typically done. 1. Elastic constants and mechanical response. In an MD simulation, a small strain can be applied to a material, and the resulting stress can be measured. The relationship between stress and strain gives the elastic constants of the material, which provide information about how it responds to mechanical stress. This approach can be used to study both linear elastic deformation and nonlinear plastic deformation. 2. Fracture mechanics. MD can be used to model how a material fails when it's subjected to stress. This involves simulating the process of crack initiation and propagation under different loading conditions. MD can provide detailed insights into how atomic interactions and microstructure influence fracture behavior. 3. Dislocation dynamics. MD can model the motion of dislocations, defects in the crystal structure that play a key role in plastic deformation, in a material under stress. By tracking how these dislocations move and interact, we can gain a better understanding of the material's yield strength and ductility. 4. Phase transitions. By simulating a material at different temperatures and pressures, MD can be used to study phase transitions, providing insights into the material's behavior under different conditions. 5. Thermal properties. The way atoms in a material vibrate provides information about its heat capacity and thermal conductivity. MD simulations can model these vibrations, known as phonons, by solving Newton's equations of motion for the atoms in the material. To compute these properties, MD uses Newton's laws of motion to predict how atoms will move under a given set of conditions. The forces between atoms are usually calculated using potential energy functions, which can either be derived from physical laws or fitted to experimental data. While MD provides a detailed, atomic-level view of a material's behavior, there are some limitations. MD simulations can typically only model a small number of atoms over a short period of time, and they assume that atoms behave classically, which may not be valid for some quantum mechanical systems. However, despite these limitations, MD remains a powerful tool for studying the mechanical properties of materials. The mechanical properties of materials are critical for a variety of industrial applications, since these properties largely determine how a material will behave under certain conditions. Here are a few examples. 1. Construction and infrastructure. In civil engineering, materials must have high compressive strength for use in structures like buildings, bridges, or dams. Concrete and steel are commonly used due to their high strength and durability. The selection of materials also takes into consideration factors such as toughness, to withstand impact loads, and fatigue strength, for enduring cyclic loads like traffic or wind. 2. Automotive industry. Materials used in vehicles need to have a good combination of strength, toughness, and lightweight to ensure safety, durability, and fuel efficiency. For example, advanced high-strength steels, AHSS, are used in car bodies for their high strength-to-weight ratio. Aluminum and magnesium alloys are also used for weight reduction. The tires are made from materials with high elasticity and toughness. 3. Aerospace industry. Materials used in aircraft need to have high strength-to-weight ratios, resistance to high temperatures, for engines and re-entry vehicles, and resistance to fatigue and creep, due to cyclic loading and high temperatures. Aluminum alloys, titanium alloys, and composite materials are commonly used. New materials like ceramic matrix composites, CMCs, are being developed for their high-temperature capabilities. 4. Semiconductor industry. In microelectronics, materials must withstand the high stresses induced by the miniaturization of devices. Silicon, for example, needs to have good mechanical properties to withstand the process of etching and doping. Additionally, the packaging materials used to protect the chips are chosen for their mechanical and thermal properties. 5. Energy production. Materials used in power plants, whether they are fossil fuel, nuclear, or renewable energy plants, need to resist high temperatures, high pressures, and corrosive environments. For instance, in nuclear reactors, materials must also resist radiation damage. 6. Biomedical applications. In this industry, the mechanical properties of materials need to closely match those of natural tissues. For instance, hip implants need to be made from materials that are strong, wear-resistant, and biocompatible, such as titanium and certain ceramics. 7. Manufacturing industry. Various tools and dies used in manufacturing processes must be made of hard and tough materials to resist wear and deformation. High-speed steel and cemented carbides are often used for cutting tools, for instance. The selection of materials for specific applications requires a careful balance of these mechanical properties, along with consideration of other factors like cost, availability, manufacturability, and specific environmental conditions. Materials science and engineering plays a key role in this selection process and in the development of new materials for future applications. This brings us to the conclusion of our presentation. Many thanks for your attention, and we recommend once more to please give a try to our Materials Square online platform for executing atomistic materials and chemical computations directly on the cloud, by visiting its website at www.materialsquare.com. Please do not hesitate to contact us by email, as shown here on this slide, in case you would like to obtain further information on the various R&D services and solutions that we provide at Virtual Lab. Many thanks again for your interest and your consideration.